I'll show you how to perform this wavelength calibration with some very useful codes that Ben, Jonathan, and myself have wrote. So the first thing that I want to do is to actually show you how an arc actually looks like. So for this, we're going to use the WASP-19 arcs that I sent you, just to familiarize you with what the typical shape of the arcs is. So here we have the WASP-19, and as you see, we have these fits files which have the arcs. They just have flux values which correspond to each pixel in each chip. Here we also have this helium, neon, and argon.dat file, which is nothing more than just a line list. So it's a line list of helium, neon, and argon lines that you're going to see now. And you also have these .txt files, which actually have the lines that correspond to each pixel. So for example, here in the first column you have wavelength, second column you have pixel, and third column you have chip. So this is saying, for example, that the line that is at 888.648, it's located at pixel 942.7 in pixel 2 in chips 2. Sorry. So that's the case for 2 pixels. So typically, an arc and a spectra actually spans 2 chips among the detector. Let's see what they look like. So to see that, you can use this lamp check lines file, which is super useful because for you it will be like having a for the. So let me just run it so you can see what I mean. So just run it, and it will ask you, well, which star. So let's play with WASP-19. And which chip? So I have chips 2 and 5 for WASP-19. So let me choose chip 2, for example. So then it will show you this plot, and this plot is just showing you the same thing that we saw on those .txt files, but graphically. So basically, it's telling you, well, this is the line at 6402.246, and the position is more or less that one. So you can see the position is not perfect; it should be around here, but that doesn't really matter because so this is what you have to get. It's only some initial guess for the position. Then the pipeline will do a Gaussian fit and fit everything all right. So as long as it is within around 3 pixels of the center, it's okay. So you see it's within 3 pixels, so it's okay in this case. So you see that the general shape of an arc, it's super easy to see. For example, you see around 5,800 angstroms. You see these 2 lines, but then it declines. You see no lines. So there's like a valley of no lines, and then you see the shortest wavelength lines around here, which are really, really small in comparison to the other ones. So you see, you can familiarize yourself with the typical shape of the arc with this algorithm. It will become in handy because, as I'm going to show you, the codes that we wrote do not work well on all the arcs. So you'll basically, for some arcs, you basically will have to just go to the arc, plot it like this without the numbers, obviously. Plot it, and then just see and check and see, for example, oh well, these 2 lines really resemble these 5,080 angstrom lines, and you'll have to make your own files by hand, just looking at the spectrum. So I'm going to show you what I mean, but at first it's interesting that you have this lamp check lines file to have a reference arc in case you need to actually make things by hand. So let's now switch to what you also have, which is the WASP-43 arcs, for which we don't have any text files. So we have to create them. So you can see that I also have this helium, neon, and argon.dat file here. It will be useful for the codes that I'm going to use. So the idea is the first. So we know the position we know the wavelength of lines that we're searching for, right? And we also know from the headers of the ARC files, like from the ones that you have, not these ones, like all the images. We know the reason that we're using them. And so with that and the binning, you can actually know what's more or less the resolution of the spectrum. So the idea is to use that information in order to map these lines into pixel space. The problem is that that has an offset in which pixel you actually start to sample this. So it's, for example, this line at 3000 angstroms located at pixel 1, 2, 3, 4, 5, etc. That's one of the problems. The other problem is that the mapping is not linear and the resolution varies as a function of pixel. So the problem is that you cannot make a perfect mapping of these things. So the idea is that at least in some very small location, that linear mapping should work more or less. So what we do actually, for starters, is to just map these lines using the Grissom information and the binning information, and then just cross-correlate it across across pixel space. And then we see where there's a maximum cross-correlation, and we have an initial guess of the position of some lines. So this is done with the guesslines.py file code. So I'm just going to run it so you can see what I mean. So I'll write this. It will ask me, well, which arc lamp you want to work with. So let's just work with comp4. It's number 3. All right. So it will load the arc files, and you'll see this. So this plot shows, in the top, you can see the complete spectrum, like the whole spectrum of the 2 chips. And in the bottom, you can actually do a zoom. So here in black is the cross correlation of the line positions from that helium, neon, and argon.dat file into pixel space. So it has been already cross correlated with the arc lamps. So you can see it matches more or less. So the positions here, they kind of match what we see in the spectra, which is the red curve. But as you go towards longer wavelengths, you can check that the cross correlation actually fails. So that's because, as I was telling you, well, first, the gap between the chips is not included here, and second, the resolution is not linear, so it's not the same for each position in pixel space. So you see the cross correlation there is worse, but then as I come around here, the cross correlation seems to be really good. So we're going to use these initial lines that we have identified thanks to this algorithm as an initial guess for the lines. So what you do, you just follow the instructions that appear here. Well, it's not really visible, but you have to basically with your keyboard just match R where you see the data, the position in which you see the data, and B of black where you see the position of the mapping of the lines. So in doing that, this will save a text file that will save the positions that you actually marked. So for example, I think the position of this line here is around here, so I'll mark red with R, and then I'll mark B, which is this is the position of the line of the mapping. So you see the two of them are marked, and this will be saved into a text file. So just repeat the same thing for all the lines. So this is around here, black is here, this is red, black, red, black. So I'm just gonna run through it. So around here it's actually easy, but you see that as you go to longer wavelengths in this case, the lines get, so the actual predicted positions of the line actually get worse and worse, which kind of makes sense for what I just told you before. So alright, let's just identify these ones and we'll be done. And then when you're finished, you just close this thing and it will save. So it says, well, this has been saved to comfort guesses. So if you open that file, you'll actually see that the positions that I marked are defined here in the same format as the of what you want as your final .txt files. So now we turn to this getLines interactive code. So the idea is that you actually use this guess in order for that code to actually fit the position of the line, and it will try to predict with a linear interpolation other lines that we were not able to match with our cross correlation with the guessed lines. Now the problem with that algorithm is that it needs at least two identified lines per chip. The problem, as you see, is that we have only we have lots of lines in chip 4, but we have no lines in chip 7, which is the other chip of this comparison star. So we'll have to actually check that lamp by eye. So I'm gonna open another terminal to this. So I'm gonna change it to this directory. So what I'm going to do is open it with Python. That's my preferred code. You can just use whatever you want. So I'm gonna open that chip 7 just to see the positions. I'm gonna plot this. So right, I have a plot. So these are the arcs of chip 7, right? So now I have to identify at least two lines by eye here. So for that objective, I'll use the WASP19 lines, right? Because we know the lines there, and we can plot it with the lamp check lines algorithm. So I'll just play with WASP19, and I'll try chip 5, which is the longer wavelength file, as you will see now. So you see, this one has the lines with the longer wavelengths, and it more or less matches what I'm seeing on the WASP43 lines. So for example, these two ones, bigger ones, are actually these two ones. These around here. So I'm gonna do a close-up around here. And a close-up here too. So you see this one, these two ones match. So sorry, that one matches this one. And then these three lines here match these three ones here. So I'm just gonna open this guess comfort guesses. I'm gonna add them, add those lines by hand. So I'll add this 7032 4131, and this one is at position. So I'll just do a close up here. This is the position, right? So it's shown here below. So you'll see it's 123.23. 123.23, and then it's chip 7, I think. That's what chip 7. So then I'll do the same for another line. So I'll choose separated one like this one here. So this one corresponds to this one. So it's 7635.106, and the position in pixel space is around 358.76. 358.76. And just to help a little more the algorithm, I'm just gonna choose two other ones around, so far away from the ones that I just identified. So let me see. So these two here are these two here, and this big one here, it's that big one there. So I'm gonna pick that big one first at 8,000 angstroms. This one, oh, it's two actually. So that's nice. I'll just put those two. So it's 8115 5.31, and this it's at position 5.44.167. 167.7. I'm gonna just, because they're too close, because they're close, I'm just gonna make the other one now that I have the chance. And this one is 539, 67, 539, 99, 539.99, 7. Then, just gonna choose that same range again, and I'm gonna do this to chart. So I'm gonna choose this tree here. So it's 1929674. Position is this one, 930, 7, and I'm gonna do the other one just to be a nice guy with the algorithm. This one. So this one is 9657.3863. Then this is, so by eye it's 1134. So alright. So I have now identified at least 2 lines per check. So now I can just run the get lines interactive algorithm. So just run it, and it will ask me, well, which star you want to work with. So I'm working with comp4, so I'll just choose that one. So alright. So here the idea is that it will show you a close-up to a line, to a predicted line at least. So you see it's predicting it's around here. So it will ask you, like, is prediction for this line within the line that it's shown there? So you can either say yes if the prediction is good, no if you think it's nowhere near, or you can suggest a new pixel center. So for example, we suggest a new pixel center because I know, so because it's around here, the closest line is this one. So I suppose this is the one. If you by chance select one line that it's not actually the line for that wavelength, don't worry, because the fit will be done with lots of lines. So one line off is not that much of a problem. So I'll select 941, which is the position in pixel space, in X space. So it will fit a Gaussian, and it will ask you, well, is the center good? Well, yeah, it's super good. So then we go to the next one. So here I don't see any lines around here. So this might be the line, but I'm not sure, so I will just put N. No. Again, here, maybe it's this line. Not sure. So I'll just ask. So just put no. Here, it's hard to tell also. So no. So if you're not sure, just put no, because then you can go through all the lines, and then it will ask you, well, would you want to go again with a better fit? Like, because you will identify more lines now. So you can do this over and over again until you feel satisfied that you identified most of the lines. So just put no, no here, nah. So here I have a line. So the position, maybe I'll just 1399 because it's 1398. It's a little bit to the right. So yeah, nice fit. So here again I will suggest 1413 as a good center. So yeah, this can work like that. So yes, and then you see we start to see the lines that we identified with the first code. So it's the predictions are pretty good. So just go straight with yes, yes. So you see the lines are more or less good. You have to be careful with this line. Just write it around. This line is actually this one, which is super small. You can do a close-up if you want. And it's really hard to fit by eye. So let's you'll see why. So I can just put yes, but then the algorithm kind of fails. So is the center good? Nah, super bad. But the initial position was kind of good, so it's no problem. For this one, yes, it's good. Yes, good. Yes, it's good. You can just continue, right? So now, once I finish with this chip, yeah, all right. So it says, okay, done with chip 4. Would you like to recalculate the fit and then find more lines? So yeah, sure. I will especially want to identify the first ones, right? With the lines I have already identified. So we'll go with yes. And it will ask you for a fit of yours. So it's asking you actually, so you have position in pixel space and you have wavelength, right? So then the wavelength solution is the function that you're going to actually fit those two things that you just measured. And it's asking you for the order of the fit. It's just a polynomial fit, a normal polynomial fit. I usually go with uneven orders. It works better, so you can understand why. But I'll just go with third order fit. So okay, let's do this again. So again here, apparently the fit was a bit off, but I can see this line here. So I'll just put the position here. Yes. So you see now that the lines start to appear close to the points. So in the past, predictions were pretty bad, but now they are kind of starting to match. So for 147, it's around here, right? So yes, nice fit. Here the line is in 1165, more or less. Yeah, nice fit. This line, I'm not sure. Just put no. This one, I'm pretty sure it's around here, right? So it's yes. I don't know. That's not a line, dude. So this 138.5. Wait, just if it could work without that. 1412. Yes. So now I'll just go through all the lines that I had already predicted. So let's suppose now that you're happy with all those fits. So you just want to move to the next chip, right? So then he will ask me now, after I finish with all these lines that I'm going to just skip because the fits are really good. It's going to ask me again if I want to recalculate a solution. I will say no. I'm happy with what I have. So okay, now it's working with chip 7. So now we changed to chip 7, and it's the same process basically. Just that you just skip the lines that you're not sure. This one I can just understand it's around 97. Good fit. So you just can't continue like this all the way, right? I'm not sure with that one. I'm sure with this one, right? So once you do this, it's just a matter of saving the file, basically. So it will save the file. It will save these final files that we need. Whoops, no. So you see the algorithm, it's kind of messy when two lines are close by. So just kind of skip them. Just fill them by hand at the end. Or you can actually, so a little trick is, so for example, in this case, if the lines are too close together, so you can tell the algorithm that the center is around here, for example. So far away from these two. So I'm gonna tell it it's around 507, for example. And it will fit the closest one, which is that one. So that's a good trick. So here the trick is by itself. 5, 4, 5. Yeah, alright. So you see the algorithm, it's pretty nice. Once you have identified a couple of them, it's actually pretty easy to just go through all the other lines. You might be wondering, well, why can't you just automatize this? Well, you see the fits sometimes do not agree at all. So you have to make sure that you're selecting the lines that you actually want to fit. So I'll just assume I'm happy with what I have. So I'll put no. And then you see it's saved at this comp4 lines. Chips.txt. So we have our first wavelength calibration guess. So the thing is that you have to do the same thing for each star. So you see I took around 10 or so minutes. So it's taken around an hour to do this. So that's it. This is the calibration steps that you have to do. If you have any questions, just let me know. Have a nice evening reducing these things.